So for the rest of the week, we will discuss a few general features of the finite element analysis, especially with regards to linear elastic problems. So the first thing that we are going to discuss is the issue of ill conditioning of the global stiffness matrix. Of course, we know that if the global stiffness matrix is ill conditioned, then we won't be able to invert it, or we won't be able to invert it accurately, and that will cause problems. So we need to make sure that our global stiffness matrix is not ill conditioned. So how do we do that? Let's look at a very simple system, system of two springs, and these has 3 degrees of freedom, and these points can move only in the x direction. So the nodes can move only in the x direction. So there is only 1 degree of freedom per node. Uh, so we can easily assemble the stiffness matrix. The stiffness matrix would be a 3 cross 3 matrix. So from the first element, we will get K1 minus K1 minus K1 K1, and from the second element we'll get K2 minus K2 minus K2 K2. So these would be my degrees of freedom, u1, u2, u3, out of which u3 is given to be 0, and this would be equal to p0 0. U3 would be 0, so I can remove the last row and the last column. So finally this will imply for u3 equal to 0 a simpler system, which is k1 minus k1 minus k1 k1 plus k2 times u1 u2 equal to p0, which is of course two simultaneous equations. It's a very simple system, two simultaneous equations in u1 and u2. So this is the system of equation that we get. Now think of a situation where k1 is much greater than k2. So k1 is much greater than k2. I have actually taken an example, but before that, let us look at the first equation. The first equation is k1 u1 minus k1 u2 equal to p. The second equation is minus k1 u1 plus k1 plus k2 u2 equal to 0. These are the two equations that we have. Now imagine that we are doing Gauss elimination to this simple system, though we can of course solve it by ourselves, by hand. We'll still do the Gauss elimination. In Gauss elimination, what we are going to do is, in the first elimination step, we are going to multiply this by 1 and add it to the next row, and we will do the same to the right hand side as well. So when we do that, this will remain k1 minus k1, and then I'll add it to this. This will become 0, and this will become k1 plus k2 minus k1 u1 u2, and this will become p. So this will cancel. So k2 u2 is equal to p is the first equation. So k2 u2 equal to p is the first equation that we will just solve from this, and then put u2 back in the first equation to get u1. So this is what we are going to do in Gauss elimination. Now that's kind of simple. Now in the situation where k1, let's say, is equal to 1 and k2 is a very small number. I've just taken k2 to be 10 to the power minus 6 times smaller than k1. And now this equation, in this equation, you will have k1 is 1, k2 is 4.4444 into 10 to the power minus 6, and k1 is equal to 1 again, and therefore this equation will now become 1.1 2 3 4 5 6 4 4 4 minus 1, which will yield 0.1 2 3 4 5 6 4 4 4 4 and so on. So this is what it will yield. If your computer can store 7 digits after the decimal, then it will store up to this. If it can store, let's say, so you will have, you need to have K2 U2, but instead you will have this much, which retains only one significant digit of K2. Uh, on the other hand, if your computer is even older and it can store only 6 significant digits after decimal, it will store 0. It will store only this part, and obviously U2 will not, you will not be able to determine U2. U2 will be taken to be 0. U2 will be taken to be infinite, I'm sorry. So this situation arises because you have a tremendous difference between K1 and K2. You have a huge difference in magnitude between K1 and K2, which is like having a very stiff spring connected to a very weak spring. And due to this huge mismatch, you will have a numerical ill conditioning in the computer because of its finite capability to store digits after decimal, and this can lead to serious problems in your finite element solutions. And this is the problem of numerical ill conditioning. And what happens is, this of course will not happen in the other case when K2 is much greater than K1. In this problem it will not happen for K2 greater than K1. So if K2 is much greater than K1, then K1 will cancel out and you will get K2 U2 exactly. So when K2 is much greater than K1, the two equations that you have, here, this is the first equation is K1 U1 minus K1 U2 equal to P, and that equation is this straight line. In the U1 U2 space, this is the straight line. And the second equation is minus K1 U1 plus K1 plus K2 U2 equal to 0. And the second equation is this, and they have a very clear intersection, and this is your solution to U1 and U2. On the other hand, this is a well-conditioned system and this can be solved. On the other hand, if you have a ill-conditioned system, but if K1 is much greater than K2, then in this first equation, the first equation remains the same, K1 U1 minus, so it remains K1 U1 minus K1 U2 equal to P. The second equation is minus K1 U1 plus K1 plus K2 U2 equal to 0, and then K1 is much greater than K2, so this is almost equal to like K1 U1 plus K1 U2 equal to 0. This almost boils down to this in the case where K1 is much bigger than K2. And in that case, you have this situation where the slopes of the two lines are very close to each other, and then you do have an intersection, but the intersection is very sensitive to the storage capabilities of your computer, to the finite floating point arithmetic that your computer uses. Of course, modern computers don't store 6 digits or 7 digits. They store many digits, but still this is a problem that you need to be aware of. Okay. Um, So what we have demonstrated here is that if you have a big mismatch in stiffnesses between elements, then you might run into the problem of numerical inconditioning due to floating point arithmetic of the computer that you are using. Now, there's a way of formalizing it, and we have mentioned this before, that there is something called a condition number of the global stiffness matrix. So this is the global stiffness matrix, and the condition number of that global stiffness matrix is C, which is simply the ratio between the maximum eigenvalue of k to the minimum eigenvalue of k. And larger this number is, if this number is very large, it indicates ill conditioning. So um, K inverse is dominated. So if you take K inverse now, then its maximum eigenvalue will now become lambda min, and its minimum eigenvalue will be lambda max. So K inverse will be dominated by lambda min, whereas K is dominated by lambda max. So the condition number of K inverse will be lambda min by lambda max, of course. Now, there are some thumb rules. The thumb rule is that suppose D denote the accuracy up to which your computer stores decimal digits, floating points. Uh, so um, it is the number of digits after the decimal that it stores. Okay, and then D loss, this is the number of digits that are lost due to the condition number of due to the large condition number that you have in your mesh. So if you have a very large condition number, then D loss denotes the loss due to the condition number, and the thumb rule is that the D loss has to be less than equal to log 10 of the condition number. So now suppose a situation where you have a very large difference between lambda max and lambda min, and this is equal to 10 to the power 8. That means your D loss will be less than equal to 8. Okay, if your D loss is less than equal to 8, so this is less than equal to 8, and I know this. Let's say my computer stores, like many modern computers do, up to 14 places of decimal, in which case my accuracy of the solution, that means accuracy of the field variable degrees of freedom that I find from my finite element solution, will be greater than 6. So I can trust them up to 6 places of decimal. Above 6 places of decimal, they are not trustworthy, because above 6 places of decimal, they are influenced by the condition number. The inaccuracies in the condition number, they will be affected by that. Remember, this is an upper bound estimate. So in general, in practical cases, this just says accuracy will be greater than 6. Okay, you will get at least six significant decimal digits which you can trust. From the 7th onwards, they are not trustworthy, but in general, since this is an upper bound result, uh, in modern computers, you can trust much more than 6. So the accuracy will be generally much greater than 6. The loss, therefore, will be less. This is the loss that you calculate from here will be less. Now, if your condition number is lower, that means you have a lesser difference between lambda max and lambda min, then of course your D accuracy increases. D accuracy increases, and you can trust your results much more. So it turns out that we can relate the condition number of the global stiffness matrix to the parameters in the mesh. So H max is the spacing, is the maximum spacing between two nodes, two adjacent nodes in the mesh, and H min is the minimum spacing. NELS is the number of elements in the mesh. 2m is, I'll explain what 2m is in a moment, but you have to remember that a large condition number does not necessarily mean that your problem is unsolvable. For example, in this example that we saw in the beginning, when k1 is much greater than k2, you have numerical problems with ill conditioning. But when K2 is greater than K1, you don't have ill conditioning problems. But in both cases, the condition number will be high. This is just an example to show that the condition number is not the only thing that determines whether your problem is solvable or not. But it's a good idea to have an idea of what the condition number of your system depends on. Here this 2m is the highest derivative in the governing differential equation. So if, for example, displacements are what you are solving for, then in a beam problem, this displacement that you solve for is the vertical displacement W, the vertical displacement of the beam, and your governing differential equation contains del 4 W del x4 in a 1D beam problem, in which case 2m is equal to 4. Okay, uh, and then n is the dimension of the system. So in case of a beam, it's a 1D system. So 2m by n is equal to 4. Okay, so for a beam, if you increase the number of elements, uh, say uh, say uh, 2 times, then your condition number will increase 16 times. So that's what this term tells you. In case of a bar, uh, you are solving for the axial displacement u, and your governing differential equation contains uh, second order derivative. So 2m is equal to 2 in this case, and therefore 2m plus n is equal to 2. N is equal to 1. In plane strain or plane stress, you are solving again for displacements, and your governing differential equation uh, contains second order derivatives of displacement. Uh, so then again, your dimension is 2. So 2m is equal to 2, n is equal to 2. Therefore, 2m by n is equal to 1. So if you increase the number of elements, if you double the number of elements, your ck in that case will increase only 2 times. However, you can also increase ck by, say, grading the mesh. Instead of using uniform sized elements everywhere, if you use, say, you have a plate with a hole problem, and close to the hole, you know that the stresses and strains are varying very rapidly. So you use very finely meshed elements close to the hole, and far away from the hole you use large meshes. That is called grading. And if you have a graded mesh, then your H max and H min can differ by quite a bit. So suppose it is a factor of 10, then for the beam, so if you graded it by a factor of 10, H max by H min is of a factor of 10, and then 2m is 4 in case of a beam. So 4 minus 1 is 3, and therefore grading the mesh will increase your condition number by 1,000 times. So if you grade the mesh and at the same time double the number of elements, you, in a beam problem, you will end up increasing your condition number by a factor of 16,000. Now, in problems in elasticity, this constant B depends on 1 by 1 minus 2 nu. So B goes to infinity when nu tends to 0.5. So condition numbers are also known to shoot up when your Poisson's ratio is close to 0.5. So all these facts increase your condition number, the number of elements, the size between the largest and smallest elements in your mesh, and then the order of your problem, what kind of derivatives you have in a problem, and the dimension of the problem. So this is an useful formula, and there are formulas that are proposed in the same paper on upper and lower bounds on the condition number for a particular problem, but these formulas are not used generally in commercial finite element codes because of computational cost. These are expensive to determine, and but it's useful to know that if your mesh and the number of elements and the kind of problem that you are solving does contribute to your condition number. You can estimate the condition number from parameters related to your mesh.